This is Barrett Givens, and in this video, we're going to practice finding closures of sets in the standard topology. So I have 4 sets here, and we want to find the closure of each one. And it will help us to think about the theorem that characterizes what the closure is. So the theorem says that a point is in the closure of a set V if and only if every open set containing the point intersects with V. It has a non-empty overlap with V. If I were to draw this in a Venn diagram, say I take my set V and I take a Y that's sort of close to V, then any open set U that I draw, if that open set contains Y, it has to touch V. Okay? So if Y has this property that every open set I draw around it touches V, then that means Y is in the closure of V. All right, so let's see this in action. Let's see this in action on these sets. So A. Let's let A be the interval 0 to 1. Well, first of all, also remember that in general, a set is always contained in the closure of the set, okay? So all of the points from 0 to 1 are already included. And when we're forming the closure, we're generally just like taking the set and then adding stuff to it, okay? Or maybe it stays the same, who knows? But generally it'll either stay the same or have more stuff added to it. So if I think about A goes from 0 to 1, all of the sets that are in A already are definitely in the closure. So now let's just think about the endpoints and then the points below 0 and the points above 1. So first of all, let's think about a point above 1. If I take a point above 1, say here, can I draw an open set around that point? Can I draw an open interval around that point that doesn't touch A? Yeah, I could just take whatever that number is and just take half of the distance between 1 and that number. I can draw an open set around that point that doesn't touch A. So that point is not in the closure. Okay. What about the point 1? What about the point 1? If I take the point 1 and I draw an open set around 1, will that open set have to touch A? Yes, no matter how small I draw that open interval around the point 1, there will be some points to the left of 1, which means it touches A. So 1 is in the closure. So 1 is in the closure. Similarly, you could show that 0 is in the closure, and points less than 0 are not in the closure. And so the closure in this case, the closure of A, it's the original A, but added in the 2 endpoints. So it's 0 and 1. Okay? And let's just remember from an earlier video that the interior of A is 0, 1. Okay. Now what about the set B? B is the set closed at 0, opened at 2, that interval, unioned with the singleton point 3. So 0, 2, closed at 3. Let me make my open interval at 2 really clear. There we go. All right, so that's B. So again, we know B closure already contains the points of B. So like the point 0 is in the closure because it's already in B. The point 3 is in the closure because it's already in B. And all the points between 0 and 2 are in the closure because they're already in B. So we really just have to think about the points that aren't in B, which one of them might be in the closure. So to be in the closure, we can use this criteria that if you take an open set U and you look at like small open intervals around the point, do those open intervals have to touch B? So for example, if I take a point down here below 0, can I draw an open interval around that point that doesn't touch B? I think I can. Look, there, I did it. Okay. So those points below 0 are not in the closure. Okay, what about the point 2 itself? If I draw any open interval around the point 2, will it contain points of B? Yeah, because any open interval that has 2 inside of it will also have some numbers less than 2. And numbers less than 2 will touch B. Okay? So 2 is in the closure. What about points between 2 and 3? No, I think you can kind of imagine if a point is between 2 and 3, you could draw a small enough open interval around it to sort of avoid 2 and 3. And then 3 itself we know is in the closure, and points above 3 are not in the closure. So the only point we have to add to get the closure here is the endpoint 2. And so the closure of B is 0, 2, union, singleton 3. So these two examples, I think, can maybe kind of convince you that if your set is written with intervals where some of the endpoints aren't included, then to get the closure, you kind of want to include those endpoints. Okay, that's in the standard topology. That is true. All right, what about C is going to be the set of all rational numbers. I want to find the closure of the set of all rational numbers. Well, every rational number is in the closure because the closure is always the set itself plus maybe more stuff, okay? But what about irrational numbers? So here's the rational numbers. And then I'll draw the irrational numbers as pink. And the thing about the rationals and the irrationals is that they're just very intermixed, like fully mixed on the number line, right? Between every two rationals, there's an irrational. Between every two irrationals, there's a rational. So take one of these rational numbers. Take a rational number like pi. Let's look at the number pi. If I were to take an open interval that has pi inside of it, take an open interval that has pi inside of it, does that open interval have to touch the rationals? Could I make that open interval so small that there's no rationals in it? You can't, because the rationals are what we say they're dense, okay, between any two numbers. So like whatever this A and B are right here, A and B can't equal pi because this is an open interval that contains pi. So pi can't be one of the endpoints or it wouldn't be included. So A has to be less than pi and B has to be greater than pi. So between A and pi, there must be some rationals. And between pi and B, there must be some rationals. So this interval has to intersect with the rationals. So what that means is that pi is in the closure of the rationals. Now, was pi special for some reason? No, every irrational number, I could have made this same argument. Every irrational number, I could have made this same argument. So the closure of Q is all real numbers. Okay? And then one more. D is the set of 1 over n such that n is a natural number. So D looks like 1, 1/2, 1/3, 1/4, 1/5, and so on. Okay, so the closure of D definitely has to contain all of these points because the closure of a set always contains the points of the set. But the question is, are there any extra points we have to add? Or is closure of D just equal to D? Okay. So for example, if I looked at a point up here, more than 1, I can put an open interval around that point that doesn't touch D. What if I look at a point between 1.5? I can put an open interval around that point that doesn't touch D. What if I look at a point between 1/4 and 1/5? I think 2/9 is in there. If I zoom in, if my pen were smaller, I can make a little open interval around that point that doesn't touch either 1/5 or 1/4, doesn't touch D. What if I were to take the point -1? I can take an open interval around -1 that certainly doesn't touch any of the rest of those points. Okay. So maybe no points get added to the closure. Maybe D just is its own closure. No, there is one more point that we have to add to D. If you think about the point 0, this is not exactly to scale, okay? If I take any open interval around 0, it'll have some negative numbers and some positive numbers. And if I keep labeling the points, like call this B, okay? If I keep looking at the points of D, 1/5, 1/6, 1/7, 1/8, eventually they'll get small enough that one of them will be less than B, because B is a positive number, and these points get closer and closer to 0 without bound, okay? And so any open interval I draw around the point 0, there's going to be some points of D inside that interval. So 0 is in the closure. So the one point we have to add to get the closure here is 0. So the closure of D is D itself, which I will recopy, union singleton 0. Okay, so this video shows how we use this characterization of the closure, that the closure, a point is in the closure if and only if every open set containing that point has to touch the set. We can use that to figure out what points do we need to add to a set in order to get its closure. Okay, so this is an example in the standard topology of how to find the closures of sets. Thank you for listening.